This is special right triangles number 3. And when I originally did this 1, 2, and 3, I did them differently. I did it where I focused on the opposite leg, then the hypotenuse, then the adjacent leg. But at some point, I started making them all the same. So this one's going to look a lot like the last two, and it's basically a repeat of that. But just from the name, what do you know about the name? What type of triangle are we dealing with?
Special right triangles.
So first of all, here's your right triangle. What makes it special? If this is 30 degrees here, what does this angle end up being up here?
60.
30, 60 is 90, plus 90 is 180. That's your total number of degrees in a triangle. I always say it's kind of fun because, you know, if you look at the bark on a tree, it's random, and so don't we live in a random universe, right? And then all of a sudden, here's triangles. And every single triangle, no matter which way you draw the shape, always adds up to the same number of the interior angles, 180. So here's a consistent factor of the universe, right? Where this is what we base a lot of our development on, right? We find the consistent aspects of the universe, and then...
We were just talking about this.
So I guess it stopped. Is it still running? Yeah. This will just be one of another example of, is it still running? You left it? Yeah. This will just be another example of the consistent aspects of the universe, is the fire alarm twice a day for no good reason other than, I don't know what, a sensitive sensor or something. Okay, so special rights. That's why we call this one 30, 60, 90. Right, there you go. Why is it special? Because it has consistent ratios to the side lengths. If you know one side length on a 30, 60, 90, you know all the side lengths. And this is what's so exciting about it.
Please disregard false alarm. Please disregard the alarm. False alarm.
No. All right, we got the hang of it. Okay. Okay, so here's your ratios. X, 2x, and x radical 3. Now I want to point something out. This side is called what?
Hypotenuse.
Hypotenuse. And what are the two characteristics you know about the hypotenuse?
It's the longest side. And
Longest
it's across
side.
the 90 degree angle.
And it's not touching the 90. Good, I like both that. And you may say not touching the 90 means it's across from the largest angle. Largest angle is 90. So it makes sense that if you open this up and this was the largest angle, it would have to be the longest side to stretch across there. Does that all make sense sort of intuitively now at some point? So look at these dimensions. Is x the longest side? Which one's longer, x or 2x?
2x.
2x. So it can't, this side can't be x, because part of this is which are the ratios, right? Which one's which? How do I know which side? And I don't know if you've calculated this on your calculator, but if you take a number times radical 3 is 1.3 something, right? 1.13, something like that. So this is going to be not as large as this. So the fact that this is the largest side, this has to be the 2x, if that makes any sense. And then the one across from the 30 is the x, and this one's x radical 3. And this makes the pattern we keep talking about now, the third lesson in the row. And that's what we like about the 30, 60, 90. And then we run through 3 examples. How do you use this to find the sides? Right, and I'm tempted to just go for it in the same way. 30 degrees, 30 degrees, and 30 degrees. These are your 3 cases. So somebody give me a dimension. Let's name this side. Just make up a problem. How long? Give me a number for this side. What do you want to do? 8. So here's a 30, 60, 90. We know that the side's 8, and it's this one across from it. It's the x. So how long is this side?
16.
How long is this side?
8 radical 3.
8 radical 3. Does this all make sense? Does your brain go, I see it now, I see why? So let's go to this side. Name the length of this side. Let's create it.
14.
14. How long is this side?
7.
How long is this side?
7 radical 3.
Hence the brilliance of this, right? Now I told you this was really hard, and these look, now at some point you're like, that's pretty simple now. The hardest side is if they give us this one that matches up with the x radical 3, because then we got to go back and figure out what x is to equal that side length. So make up a side length here, and I'd love it if it's divisible by 3. That way we get to reduce it as we go through. Give me a number divisible by 3.
15.
15, that's fine. So for this side to be 15, something has to be multiplied by radical 3 to equal 15. So we're working in reverse. We're asking what times radical 3 will equal that 15. And whatever it is, it has to be the length of the side. Because this side times radical 3 is producing the 15. And hence, we put them equal. So we say x radical 3 equals 15. We divide both sides by radical 3. And the algebra is quite consistent here. We need to rationalize the denominator. So we pick radical 3 over radical 3. Why? Because that's 1. Any number times 1 remains the same value, so it's a legal move in math. We pick radical 3 because radical 3 times radical 3 will produce a radical 9, and radical 9 is 3, so that'll disappear, so to speak, the square root symbol from the denominator, which is what we're trying to do anyway. It's a simplification technique. 15 times radical 3 is across the top, or numerator position. X here is still equal to 15 radical 3 over 3. 15 divided by 3 goes in 5 times, and the radical 3 is still there. 5 radical 3. This is the hard part for students to get. If x is 5 radical 3, that's what x is. And this side is x. How long is this side?
5 radical 3.
Does this make sense? What students will often want to do is say 5, because their brain is now back thinking some number times radical 3. But it has to be the 5 radical 3. Why? Because it's now being multiplied by radical 3 in this setup, right? So x is equal to 5 radical 3. It goes in exactly for that side, just like we did. But just to prove it, 5 radical 3 is what x is times radical 3. Radical 3 times radical 3 is 5 radical 9. Radical 9 is 3, so 5 times 3, does this equal 15? Check. So this whole piece, x, has to be the 5 radical 3. We need the radical 3 in there because that times radical 3 equals 15. I don't know if I'm explaining it very well, but does this kind of make sense? Kind of see the logic? Okay. And then if this is double this, what do you get?
10 radical 3.
Everybody repeat after me. Nice, I heard somebody do that. That was good. Did you hear that? Was that you? Oh, somebody. Oh, nice. That was good. I can't see anybody's mouth moving or anything. That was very nice. Okay, and that's it. That's special rights. The only other thing you can do from this point is start to flip everything around, right? If you, let's just do one example. If we flip the triangle around like this is still 90, and this is now the 30. Tell me where the ratios go. What's the length of the hypotenuse? You're doing the pattern now. What's the length of this side?
2x.
2x? Is this okay with you guys? Do you see that? 2x. What's the length of this side? Hang on a second. What's the length of this side? And you're looking at this one, right? You're trying to figure out which one is which. What's the length of this side here? Yeah. And even with, look how badly I drew the triangle, right? So it's your brain is getting a little bit, I'm trying to confuse things slightly, right? It's a bad drawing, but what you're doing is orienting the 30 degrees. That means this one over here is 60 degrees, right? So now I know the orientation here. It's the one adjacent to the 30, and this is the one adjacent to the 30. So x radical 3 is correct, right? And then across from the 30, or opposite, this has to be the x. So that's all we have now, is just taking this thing and manipulating around. Otherwise, the special right triangles, once you see the vision of them, they simplify. You don't have to use any trig functions on this. You can use sine, cosine, and tangent, just like we've always studied, but that's sort of a longer process. If I can just figure out a few numbers, and if you practiced this enough, this would start to become clearer to you. You could start to do this calculation in your head if you did enough of them. We probably won't make you do that here, but when I was a kid, they used to make us do like a whole list of problems, right? Every night, it seemed like. Okay.